All right, so this video, this is that good stuff right here. So this is when we're talking about the three-dimensional structure of alkanes. So this is where organic chemistry gets pretty difficult and is going to take a lot of practice because we tend to write chemistry on paper, right? So just in 2 dimensions, but in actuality, chemistry works in 3 dimensions, as does pretty much everything in life, because all matter is 3 dimensions. And so when we are talking about structures of alkanes, we want to bring up the concept of stereochemistry. And stereochemistry is basically when you have the 3 dimensional structure of something. And conformation is also another vocabulary word that we're going to need to know, and that's basically the orientation or the arrangement of a given molecule. Okay, so they tend to go hand in hand, but first let's go over conformation, and we'll kind of show you what we mean by that. So the first molecule that we want to kind of discuss when we're talking about conformation is ethane. So this is CH3, CH3. There's just 2 carbons bound together. We can also draw this, remember, with our wedges and dashes. And then we've got our hydrogen, 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 and hydrogen. Okay, so also remember that the wedge right here, the one that I've highlighted in red, those are sticking out at us. Those are sticking out of your computer screen, while the dash, those are sticking into your computer screen. Okay, sorry. And then this particular bond right here, and right here obviously, those ones are just laying in the plane of the screen. Okay, and so this is one way that we draw organic molecules in a 3-dimensional pattern, and to kind of depict that 3-dimensional aspect of the molecule. And so what we want to do is kind of introduce the different conformations of ethane, and along with that comes something called a staggered conformation. Staggered conformation, not confirmation, but conformation, and also an eclipsed conformation. Formation. Sorry. Okay, and so what this is going to require us to do is actually take a look at, let's see if I could draw this. Let's say we got an eyeball. Check out this eye. Ooh, look at that eye. That looks gorgeous. Of course, you gotta have those long eyelashes. And then what we're doing is we are ideally taking our molecular modeling kit, and we are looking straight down this red chemical bond, down this carbon and this carbon, and we're going to look at the orientation of the hydrogens that are on those respective carbons. And so what we can do is we can rotate about this sigma bond, and that puts those hydrogens in different positions that are either going to be staggered or eclipsed. Okay, and one more vocabulary word I kind of want to give you is a dihedral angle. Dihedral angle. Okay, and that's basically the angle that we have between 4 different atoms. Okay, so 1, 2, 3, 4, for example. Okay, and so these will all be more clear as to what they are. That we're going to define these terms as I show you an actual structure. I'm going to show you a structure that I have built with my molecular modeling kit, but I'm also going to show you using a JMOL program that I found online. It's pretty fun to use. And so first, let's take a look at the molecular model. All right, so hopefully we can kind of convey this information as well as possible in this format. I got a video, or I got a modeling kit that I've prepared this particular molecule with. So if we look at it, this black atom right here is a carbon, and then the white ones are hydrogens, and we've got a carbon with 3 hydrogens on one side, and then a carbon with 3 hydrogens on the other, right? Put the two together with a sigma bond, a single bond, and now we've got ethane. So this is the molecule that I've drawn for you. And remember, these chemical bond, or these this CH3 can kind of rotate about this sigma bond because it is a sigma bond, and so this is what we mean by having the ability to rotate. And so what happens is we get 2 different conformations that we wanted to discuss. And so the first one that I told you about was staggered, and the second one was eclipsed. So let's talk about staggered first. Okay, so staggered is basically when we have, see, this is basically how I drew the structure for you. We have a carbon here with a hydrogen that's sticking up and one that's down, and those are in the plane of the screen, while this one right here is poking out at you, and then this one right here, which is a little bit harder to see, is kind of coming back away from you. Okay, and so we also have the wedge on this side coming out at us, and then the dash coming away. Okay, and so drawing it like this actually gives us what's called the staggered conformation. And so it can be defined as in a couple different ways. So one of them is if we're focusing on this CH right here that's sticking up, this CH bond is said to be bisecting the CH2 on the other side. Okay, so if we rotate this, so remember I said you're going to look down this carbon-carbon bond, so depending on which side we look at, but if we want to, what we can do is see this original CH that's sticking up, it's bisecting the CH2 here, and so meaning that it's kind of split right down the middle in between that CH2 or those 2 hydrogens. Okay, and so one of the other terms that I gave you is a dihedral angle. Okay, so what I want to do to kind of emphasize the point is I'm going to switch out 2 of these hydrogens for green, and so that way we can kind of keep an eye on what I'm referring to. Okay, so now what we've got is a hydrogen sticking up and a hydrogen sticking down, right? Sorry, let me adjust that a little bit. So we've got the ability to rotate this bond, right? And so what we want to do is kind of put it in that staggered conformation that we saw a minute ago, where this hydrogen right here is bisecting these 2 hydrogens here, coming straight down the middle, right? But also notice, if we're looking at the green hydrogen atoms, this one with respect to this one, this is actually, it's hard to kind of pinpoint that, but if you look at this one right here, the goal is to kind of indicate that one full rotation would be 360 degrees, right? And so if you think of each of these as 120 degrees, so that's a 120 degree rotation, that's a 120 degree rotation, that's a 120 degree rotation, right? Let's say we only did a half of that rotation, right? So that would be a 60 degree rotation, right? We can also go in the other direction, a 60 degree rotation, okay? Because that was like a half of an adjustment there, okay? And so the reason why I'm pointing this out is because I just want to make it clear that the angle between this one and this one, from your perspective, is only 60 degrees, okay? And so that dihedral angle between these green atoms, that's 60 degrees, and that's another definition of staggered conformation. So yeah, we can have that bisecting, this hydrogen bisecting these 2 hydrogens here as one definition, and then we can also define it as having that 60 degree dihedral angle here. Okay, and this is just because this is the closest kind of atom to it if you were going to kind of search around in a circle. Okay, So notice when I was rotating this particular molecule, I was rotating around, and there is a certain point where everything is covering. So like these atoms in the back are completely covering the ones. These atoms in the front are completely covering the ones in the back, right? If I can make it perfect, right? Depends on your perspective. But this is actually the other conformation, the eclipsed conformation. Okay, and that makes sense now, right? Like if you have an eclipse, that means like the moon or like the earth or whatever is going to just be getting in front of the sunlight. And so that could cause either like a lunar eclipse or a solar eclipse, for example. And so these guys are eclipsing the back atoms from our point of view. And so this is the eclipse conformation. Okay. Now, what's the dihedral angle between this guy and this guy? Okay. So again, if we're kind of going over the degrees, right? So this is 60 degrees, and this right here, if we're going in the opposite direction in 60 degrees, basically there's no difference in the angle between these two, right? And so this is actually a 0 degree dihedral angle. And so that's another definition that we can apply for the eclipse conformation. Now, one thing I want to point out now is this type of bond rotation and using the word dihedral angle. This is 60 degrees. This is back at 0 degrees now, right? So if we're looking at the white atom compared to the green one, that's 0, 60 degrees, 0, 60 degrees, 0, right? And it took basically one full bond rotation to get the green all the way back to the green. Now, this type of bond rotation and the discussion of the dihedral angle is going to be important to visualize when we're talking about the energy states of each of these conformations. So the staggered versus the eclipse conformation. And so we will be talking about the energy versus the dihedral angle. And so that's what we're referring to when we're talking about a 60 degree dihedral angle versus a 0 degree dihedral angle. Okay, so it's really important that we are understanding this. If it says like a 0 degree versus 60 versus 120 versus 180, so these, although this and this are always, these atoms are going to be 60 degrees apart. If we're focusing on just the green atoms, that's what we mean by 60, 120, or 180, because the goal is to basically look at all the energy differences when we're going one complete revolution around. Okay, and so again, this might make more sense when we see that dihedral and the energy versus the dihedral angle, but I just wanted to point it out now while we have this in front of us. Okay, and but first let me show you kind of like the online interactive mode for a staggered conformation and an eclipse conformation for ethane, just in case you either don't have these yet, or maybe you just didn't purchase them at all. You still have something to work with online. Again, I encourage you to use whatever you can, right? So sticks and fruit, or like marshmallows or toothpicks, or whatever you have to do. Get creative. It is really important to be able to visualize organic chemistry in a three-dimensional manner, but in your head, right? And that's pretty tough sometimes. And so it's going to take practice. Don't get discouraged if you don't get it right away. Okay, but let's check it out. All right, so what we're looking at here is something called like a JMOL program of ethane. And so what it is it allows us to actually touch the molecule and rotate it around. There's obviously some limitations to this, but because all I can do is basically rotate the molecule around. I can't really rotate about that sigma bond, or at least I haven't figured it out yet. But what this allows us to do is kind of visualize that staggered conformation, okay, and what that looks like as we rotate the molecule around. Okay, now what we can do is also look at this the eclipse conformation. So we got the molecule moving around, boom, 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 but then we have the Eclipse Conformation. You can see that basically what we're doing is covering up as we look down that carbon-carbon sigma bond. So I don't know if it'll let me do it, but the carbon-carbon sigma bond, we can basically cover up the hydrogens and the carbons in the back, and that's the Eclipsed Conformation. Okay, and so this is, you can see at the bottom, it's a JMOL program. So there are different manipulations that you can do to this. I think you can even actually calculate the dihedral angles and things like that. But if you want to check it out, you can Google just ethane and then JMOL. So JMOL, and then something should pop up. Okay, so before we get into that energy diagram, what I want to do is introduce kind of like a new concept, or it's a term as well as a different way to draw ethane, for example, or other organic molecules. And it's basically based off of our point of view when we are looking down that carbon-carbon bond, kind of like we did here. Okay, so when we were trying to view that staggered conformation or that eclipse conformation, essentially the way we can draw that on paper is by doing a Newman projection. Okay, a Newman projection. Now these are quite simple, but also not. I mean, I feel like that's just chemistry in general, probably. They're pretty straightforward, but it is probably going to take some practice to kind of understand what the heck we're looking at. But once you get it, you're going to be like, oh my gosh, so simple, right? And so let's go ahead and draw out, sorry, I'm going to draw out another one of these guys, just so that we can have them side by side. Okay, and so remember what we're doing is we're looking right down this carbon-carbon bond. Okay, so that point of view. And so now if you think about it, if we're looking at from this point of view, which side of the molecule, if we divided it into two separate sections, with that, according to that blue line, I'll color it in red actually. So this one on the left side is going to be in red, and the one in black is on the right. So if we wanted to identify which molecule or which part of that molecule we see first, or which is the front, then which one do you think it would be? If we're looking from this side, then this must be the front, right? And if we're looking from that side, if that's the front, then these are the CH3, or this is the CH3 in the back. Okay, so the reason why I want to identify this is because when we're drawing a Newman projection, we are basically drawing it from that point of view, but we have a special way to indicate what's in the front and what's in the back. First of all, this carbon right here in black, that is just indicated by a dot. Okay, and the hydrogens are just a typical bond. We're not going to have a wedge or a dash. Okay, it's kind of assumed that they're projected outward at us. Okay, now if obviously, so this is my eyelashes. I guess this will be my nose right here. Boom, got a little bug hanging out. If that's my nose, then that means that this is the top, right? This is me looking upright. And so which of those hydrogens is projected upward? And which direction is it going to be? So this is where the three-dimensional chemistry gets a little tricky. If this is projected up, so I feel like that one's pretty straightforward. So that means we would draw, our point of view is looking at this central carbon with the hydrogen sticking up. Okay, now one of these hydrogens, so I'm going to highlight it in black just to show you the one that I'm focusing on. That one, if it's projected out at us, but we're looking through that let's just call it a carbon 1, carbon 2. If we're looking at down that carbon 1-2 bond, that C1-C2 bond, then this wedged hydrogen is actually going to be to our left. Okay, and so we're going to draw that to our left. And again, let me highlight this in blue just to indicate that this is the one on the left. Okay, And I wonder if I can draw this one in like a nice little pink color. Cool, I got that for you. Now this one over here is going to be the hydrogen that's pink. And so hopefully this kind of helps you determine that if the wedges are on the right side of the molecule and we're looking from the right side of the molecule, then those are going to be sticking to the left, and as this blue hydrogen is, and then if they're dashes, then they're sticking out to the right from that point of view. Okay. Okay, so now how do we draw the hydrogens in the back? And how do we draw the carbon in the back? Well, I'll answer the question about the carbon first. So we draw a circle here, and this is looking more and more like a Newman projection, but we don't actually draw that carbon because the carbon is implied. And if we're drawing a Newman projection, then it's implied that we're looking down a carbon-carbon bond. Okay, and so this carbon right here is the front carbon, and it's assumed that the back carbon is directly behind it and we can't see it. Okay, so now if we were looking down that carbon-carbon bond, we have these two hydrogens that are projected away from us and towards us. Okay, and so that means that we will have a hydrogen sticking out, and then down. Okay, so what I want to do is kind of point out that this hydrogen right here that I've labeled in black now is that lower hydrogen, right? I feel like that one's a little bit straightforward because it's sticking down and it's in the plane of the board. But let's see what color I have now. I got a poopy brown one. Let's use a poopy brown. This hydrogen right here is poopy brown. That is the poopy brown wedge that I'm drawing, and that wedge indicates, at least in this structure, that wedge indicates that the hydrogen is projected out at us. Now if we're looking from this point of view down that carbon-carbon bond, if it's projected out at us from in the way this is drawn, then that means it must be projected to the left from this point of view. Okay, so that means this is that poopy brown bond. Okay, and then the other one is just the red one. Okay, so I'm not gonna color code that one. Okay, so it might have been like a convoluted explanation of how to draw that Newman projection, but it is really important to understand how to convert a molecule drawn like this to a Newman projection, and also make sure you get the location of your hydrogens, or it's not always going to be hydrogens, it could be carbon, like a carbon or some other group there, and it's really important to be able to convert from a Newman projection to the skeletal structure, and then from the skeletal structure to the Newman projection, and back and forth. Okay, all right, so, and remember, this is a staggered conformation drawing. Okay, so this is an example of a Newman projection for a staggered conformation, and that dihedral angle, as in the angle between this guy and this guy, is 60 degrees. Okay, so now let's take a look at the eclipsed conformation. Okay, so eclipsed conformation for ethane. Okay, because remember, we're working with ethane right now, and so this is a very specific discussion for ethane. And so what I want to do is kind of show you this drawing right here, and draw the basically that kind of with the wedges and dashes, but for the eclipse conformation. And so what we can do is we're going to draw our carbon-carbon bond, right? And then generally what I would do, I like to, for whatever reason, put the bonds that are in the plane of the board both up, and then I'll have my wedges and dashes down at the bottom. Now, of course, you can kind of rotate around this bond to draw the or just flip the molecule over to have the other hydrogens, or sorry, the hydrogens that are in the plane of the board kind of on the bottom. But again, for whatever reason, I just kind of prefer, I feel like I draw it better when it's in this format, but you can also have this format as well. But in the discussion, what I'm going to do is kind of draw the Newman projection based off of that particular conformation or orientation, okay? And so remember, what we're going to do is take a look at this particular ethane conformation, and we are looking down this carbon 1 and carbon 2 bond. And so that means that what I want to do first, in order to draw the Newman projection for an eclipsed conformation for ethane, I'm going to draw that central carbon. I'm going to draw a bond up, down, and down. And so this, I mean, you can always think of it as like a Mercedes sign, right? This is more or less a Mercedes sign. But at least for the Newman projection, we have it a little bit beyond the circumference of that circle. These chemical bonds is what I mean. So like this part is breaking through that circle. I want to draw that circle again. That was a terrible circle. That's also a terrible circle, but that one's perfect. All right, so what we want to do now is basically put all of our hydrogens on there. Boom, boom, boom. And remember, these are the front hydrogens, right? And so that's this group right here. We can just label that in blue if we want. I like blue. It's easy to see, I think. And then these hydrogens that are in the back from this perspective are actually, since they're eclipsed, the way we draw them is a little bit different. And so depending on your source, they might have a slightly different arrangement, but pretty much what we're going to have is something like this. And then I think the upper one tends to be a little bit higher, while the lower ones tend to be a little bit shorter, okay? And so it doesn't look amazing. It's not pretty necessarily, in my opinion, but it does kind of, that is the way that we indicate that this hydrogen and this hydrogen are directly lined up, and this is the eclipsed conformation. Okay, so eclipsed conformation. And the dihedral angle, what do you think the dihedral angle is? The dihedral angle is equal to, remember that's the angle between basically these two, and there is no difference because they're perfectly lined up, and so it is 0 degrees, okay? Now, when we're talking about molecules in general, we can always talk about the energy associated with these molecules, and either the energy of a given molecule in the state that it is, for example, like a charged ion, negative or positive, or we can talk about the energy associated with its conformation. And so the energy of an eclipse conformation is higher than the energy of a staggered conformation. Now I want you to think about why. You can even pause the video if you want for a second, but just think for a second, why might that be? So I'm going to answer that right now. So the hydrogens, at least on the staggered conformation, you can see that they're nicely laid out, okay, spread out pretty much as far as they can get, right? And so that's a kind of a theme that we've seen before, right? Making sure the atoms are as far away from one another as possible. So that's kind of like Vesper theory, right? The valence shell electron pair repulsion. And if we have our hydrogen atoms as far away from one another as possible, then we minimize something called torsional strain. Okay, so torsional strain is the strain associated basically when we get in this eclipse conformation. So those hydrogens are kind of occupying an electron, like a space with their electron cloud. And since they are in close proximity, that electron cloud is kind of repelling one another, and this causes a torsional strain. Okay, and so that is an increase in energy caused by an eclipsing interaction. Caused by an eclipsing interaction. And I would say, think of valence shell electron pair repulsion. So Vesper theory says that you got to get these guys as far away from one another as possible, and that's going to minimize the energy. And so basically what we mean is eclipsed equals high energy, and then staggered equals low energy conformation. And so these are obviously the conformations. And if you think about everything in between, if we rotate the eclipse conformation 60 degrees, we get to the staggered. And then we rotate it again 60 degrees, and then we get back to the eclipsed. Okay? And so what that means is we're alternating every 60 degrees to get from a high and a low and a high and a low. Okay? And so what this does when we actually rotate about that carbon-carbon bond is we get a graph, and that's the energy versus the dihedral angle. Okay, so energy versus dihedral angle, and this is for ethane, remember, because the energy associated with that eclipse conformation is going to be different for ethane than it is for other molecules, because hydrogen is very small. Okay, so let's see what that's going to look like since it's an energy plot. Let's see if that makes a nice little thing for us. So this is energy on the y-axis, and on the x-axis what we're going to have is 0 degrees, and then we're talking about rotating 60 degrees to get to a new energy state, and then 120 because that's another 60, and then we're going to keep going until the ethane has completely rotated about that carbon-carbon bond, and we reach 360 degrees. Okay, which is basically back to 0 where we started. Okay, and so what we want to do is, let's say we start at a dihedral angle of 0. What conformation is that? So remember, 0 for dihedral angle of 0 is an eclipsed conformation, and so that means that we're going to have some energy state that's here, for example. Okay, and then as we rotate 60 degrees, we get to a staggered conformation. Okay, and that's going to be a lower energy state, and so we'll just draw this random dot at a lower energy state. But then when we rotate 120 degrees or 60 degrees from that staggered state, we get back to an eclipse conformation. And since all of these groups right here are the same, that means that we get back to the same energy level, which was here. Okay, and so what we want to do is draw an energy state that's, or I guess draw a point on this graph that's equal in energy as 0 degrees. And then as we keep rotating, we do it over and over again. Okay, and so what this is basically, we're connecting the dots. And that's what our energy versus dihedral angle for ethane graph would look like. Okay, and so that's pretty much it for this. One thing we need to know though is how much basically energy is associated with the eclipse conformation. And so just in general, for each hydrogen eclipsing, or eclipsed bond, we increase by the energy by 4.0 kilojoules per mole. Okay, and so what that means is if we've got, let me just erase this again for you. This is one hydrogen-hydrogen eclipsed bond. This is another hydrogen-hydrogen eclipsed bond. And this is another hydrogen-hydrogen eclipsed bond. So each one of those is associated with 4 kilojoules per mole. And since we have 3 of them, that means that this entire energy difference is 4 kilojoules per mole times 3. So that's 12 kilojoules per mole. 12 kilojoules per mole. Okay. And again, that's because we have 3 eclipsed bonds. And that's going to be basically the energy difference between this energy minimum and the energy maximum. All right, so what's this green mean? You want to talk about practice? Let's talk about practice. All right, let's try a couple problems because this stuff is crazy. What you're talking about, Jess, right now? How do I draw this? So let's take a look. First, maybe why don't we try and draw this as a Newman projection? Okay, and what I would suggest, or I guess the question needs to be more specific in that I would say that draw the Newman projection looking down the labeled carbons, for example. So I can label this as C1 and C2, just kind of like how we always have. So looking down C1, C2 like this, and I want you to draw a Newman projection. Here, let me draw my eyeball. Or I could just say Allen Iverson is looking down, but so carbon 1 is the front, so we're gonna do that, boom, and then I'll draw a circle around it. Okay, I don't like that circle. That one's a little better. It's all right. Okay, so now we have to remember also that we've got this guy and this guy. Okay, get C2 out of the way. Why are you in the way, C2? All right, so there's our hydrogens there as well. Okay, if I'm looking down C1, C2, this right here is a methyl group, and that methyl group is in the plane and it's pointed down. So that's how I would draw it. I'll draw the methyl group explicitly so that way we are understanding what's going on. And now I gotta finish my Mercedes sign with each of those hydrogens poking out. And so remember, these are all the atoms on the front, or the groups on the front. And now we have to draw the atoms in the back, or the groups in the back. And so the question that you need to answer is this, the way this is drawn, is it staggered or is it eclipsed? Well, since the bonds that are in the plane of the board, both methyls, are opposite of one another, then one is up and one is down, and so that means that these are going to be staggered. Okay, now that CH3 is the thing that's up here, and now we've got hydrogens on either side. Okay, and so this is what that Newman projection would look like. Okay, and so another thing I want to mention is oftentimes in organic chemistry we abbreviate things, and so methyl groups can actually be abbreviated with an ME, so as in methyl. And so another way we can possibly draw this is with an ME here. We'll draw all our hydrogens and then an ME here. It is a little bit easier at times, especially when you have like ethyl groups and things like that. And so There you go. That's one example for you. Let's try another example because practice makes perfect. Okay, so basically what we wanted you to do is draw the Newman projections for each of the following compounds that I'm about to draw. Okay, so draw Newman projection. All right. And then I'll indicate obviously which chemical bond we're looking down, but let's try similar, but let's abbreviate these guys, ME, and sure, why not? Okay, and so what we want to do is look down this chemical bond here coming from this point of view. I got red eyes because I've been studying so much. All right, and so now what we want to do is make sure that we're aware that this particular carbon is the front carbon. So we'll do that first, and then we'll draw our little circle. This methyl is projected downward with respect to my eyeball. So we're going down, down, in an earlier round, and then we've got the other groups on that front carbon at least are methyls, and so we're going to go ahead, since they're both the same group, we don't really have to worry about which side is which, but on that back carbon we do have to worry about. So this back carbon right here that I'm kind of highlighting in blue, that does have two different, or at least actually has two different groups on there. One of them is a methyl projected upward in this in the plane of the board or the computer screen. The other two are out and in, and so they are left and right on the bottom, and that is a staggered conformation. Okay, staggered. And let's take a look. Basically, we've got this methyl. I'm going to put this methyl here. Okay, and now what we have to do is figure out where this methyl goes and where this hydrogen goes. So, like, do I put the hydrogen here or here? And it does matter because that is it's a different compound if you don't. Okay, kind of. Let's just focus on the task at hand rather than whether or not it's the same compound. We do want to get good at indicating where that hydrogen is, I guess. And if we're looking down that carbon-carbon bond where the eyeball is, that hydrogen is going to be on our left. Okay, and so this is going to be important for us to figure out once we get more complicated molecules. Okay, I'll finish that off with the Me, which is here. Okay, that is, let's try another one. Let's see. Let's get crazy. Why not? Let's get crazy. Why not? Okay, so what we want to do is this weird molecule right here. We're going to look down this chemical bond from this side with my eyeball. Okay, now, so first things first, indicate this is the front carbon. So here we go. We got our circle. I don't like it. I'm sorry that I'm picky. That one's okay. All right, so since this right here, this particular group, remember this is an isopropyl group, that is projected downward, so we'll draw it here. And the isopropyl group, so this is actually abbreviated with a small I, a big P, and then an R. So this is the iso and then PR for propyl. So just because I don't want to draw it, you can do it like that. And the other hydrogen's got to go here, right? Now, the groups on the back. We do have this other isopropyl group here, and it's projected upward, and so we're going to have that IPR the Iber, and then we've got our hydrogens here. Okay, and so I think at least for now it's okay. Those are okay examples. And so we're going to want to get more practice in, but as we introduce another molecule and its conformations, we'll get into more complicated examples. But just wanted to do a few there for you. But that's it for now. Okay, so what we want to do in another video is the conformation of butane. So go check that out because it's a hoot.